Because, it's good to recall things. And I think when it comes to this exam, I was thinking about this exam. In some sense, it's not too bad. We have two big topics, right? We have Laplace transforms, and we have series. And so in comparison to the first exam, when it feels like we have 100 things that we have to remember, or the second exam when we've got all these matrix things and we have to remember, this one's a little bit more narrow. And I think that gives us a good shot. I'm optimistic. I think this might be our best exam yet. We'll know on Thursday. When you hand back the exam, if you can look at the instructor, that means it was a good exam. But when the instructor is has this shield of invisibility and you can't make eye contact, that's usually a sign it wasn't as good as we hoped. But all right, that's a Thursday thing. So we'll start by reminding ourselves about Laplace transforms. Now, the goal of Laplace transforms is just to really transform. You're turning one function into another function. And that's it. That's the whole idea. And you might say, okay, great. Why do we turn one function into another function? The idea is we're changing a problem in one setting, in this case, something that involves derivatives and integrals, into another setting, in this case, which involves algebra. And so that's why we do it, because hopefully we're pretty decent at algebra. Now, there's a lot of things to say about Laplace transforms, and we're going to have several slides. So the first thing we just want to start with is we have a collection of our basic building blocks. And so these are what's true about the Laplace transforms for particular functions. And so here's a collection of some of the functions that we might care about. Now, these aren't randomly chosen functions, by the way. What do all these functions have in common? Well, they're nice and they're on the formula sheet. Yeah, the stuff that you're going to see, the formulas we're going to show, are things directly from the formula sheet. So you don't have to spend time memorizing these equations. What you need to do is say, how do I use these? That's what we're after. Now, perhaps the most exotic one of all of these is when we have t to an unusual power. So you could have t to the half, or t to the e, or t to the pi, or something, just whatever. Well, that turns out it involves this function called gamma, and there's some rules about gamma. Gamma of a half is square root of pi, and gamma of beta plus 1 is beta gamma beta, which just says it behaves like factorial in some sense. Yes, there's a question.
Normal number, can you still use that formula with gamma?
So if you have a what?
Normal number, like a 2.
Well, so if you have a whole number, you use the line below it.
Yeah, but can you use it regardless?
Well, you can use it regardless, but the trick is we usually don't like to leave answers with gammas in them. And so it turns out that gamma of n plus 1 is n factorial. So I'd recommend if you have a whole number, use the formula for t to the n. Now, of course, it should be noted that all these really come in pairs. Now, what do I mean by all these come in pairs? Well, for instance, we'll just pick on the first one. If the Laplace transform of 1 is 1 over s, we can also talk about the inverse Laplace transform of 1 over s. And what would that be? 1. Right. We don't put both formulas on the formula sheet, but it's there implicitly. So you want to make sure you recognize things. And so you will potentially see a problem that says, hey, here's some functions. Take the Laplace transforms of these functions. So you want to be able to make sure you know how to do those. Now, as you see, we've got a lot of algebra here. There's this note. When doing inverse Laplace transforms, be ready for partial fractions. So, if I were a betting man, I would bet that at some point in this exam, partial fractions will show up. So you want to make sure you know how to do partial fractions. Now, there's a lot of things that one could say about partial fractions, and we don't have infinite amount of time. But I will just put a little reminder here. You have to have a polynomial over a polynomial. And what if it's not a polynomial over a polynomial? Then what do you do? Yeah, something else. That's what you do. Now, oftentimes what you can do, if you don't have polynomial or polynomial, the reason you don't have it is you have like an exponential involved. And the answer is you pull the exponential off to the side. And then so it's polynomial or polynomial times exponential and deal with the exponential separately from the polynomial or polynomial. So that's one thing to keep in mind. Okay, so we have this collection of functions, but of course it's not very exciting until you're able to start gluing things together. So then we toss in the rules. So here are various rules that you might encounter. So we actually have the definition of the Laplace transform. And we see, okay, if you multiply by an exponential, that corresponds to a shift. We have this f star g, that's f of s g of s, where what is f star g? Well, that's our convolution. And so that's another thing that can show up. Now, a few others. If you take the Laplace transform of t, f of t, that's minus f prime of s. And so we're able to handle multiplying by t. In fact, we can multiply by any whole powers of t. Just means take enough derivatives. And we can also handle anti-derivatives. So the antiderivative of f is f of s over s. And we've already said this here, but of course, these rules come in pairs. So if we have a rule for Laplace transform, we also have a rule for inverse Laplace transforms. So, I mean, we can pick on any of these rules that we want. And, okay, so here's one that gets used a lot. If I see f of s minus c, what does it say about the Laplace inverse of f of s minus c? What would that be? Well, yeah, e to the ct f of t. So whenever we see a shift going on, we know, hey, that really means that inside we have an exponential showing up in our answer. And of course, this can be done for everything along the way. So, okay, so that's good to know. And there's a note here. Many problems are like onions. You're probably like, yes, I'm going to cry. No. Not that way. They have layers. And so that means that we can combine things together. So be ready. I mean, we can just take a look at our various rules that we have here, and we can just make up an example. We just pick a couple of basic ideas. Anyone have some favorite rules they like? You can just make up a problem with layers.
Convolution.
Okay, someone said convolution. Any other rules that you like? Oh, okay. Throw in a derivative rule. Any others? Pick some functions over here. All right, e to the ct, and one other function. Oh, someone is really going crazy. T sine t. So you could imagine, we can just combine all these together and ask something like, what's the Laplace of t integral 0 to t of tau sine tau e to the t minus tau d tau? And if you saw that, what would you do? Oh, you're channeling your inner onion, I see there. All right. Cry. But then you'd say, look, no, this is an onion problem. Okay, so onion problems have layers. You just have to figure out where to start. So, what do you see here? Yeah, so this takes practice, but that's okay. That's why we practice. This part right here, we can think of as our f of t. So we have t f of t. We say, all right, well, what's that? If we simplify, what do we see this part? It's a convolution. So you say, they're testing us on a convolution rule. And then they're going to test us on a derivative rule. But we're ready. We're not going to fall for their tricks. We say, look, this is really t sine t convolution with e to the t. Okay? So that's our f of t. We say, hey, we know what t sine t does because it's on our sheet. So that goes to 2s over s squared plus 1 quantity squared. And what does e to the t go to? 1 over s minus 1. So, okay, so now we know what happens to the Laplace transform of that. So how do we get our final answer, which we probably won't work out all the details, but what do we need to do now? So let's call this temporarily, this is f of s. What do we need? So our answer will be minus f prime of s. Now, we'd have to work through what the derivative is, but in the interest of time, we won't do that. But that's how you can combine things. You can just pick a few rules, and you combine them together. So don't expect us to ask a question like, hey, what's the Laplace transform of e to the t? But expect us to ask a question like, hey, what if you combine, like e to the t and sine of t? Or maybe like t squared and a cosine t or something. Just a couple rules combined together. So anticipate. Be ready. And don't panic. We're not going to ask you things that you can't answer. You're going to have the tools. You have the formula sheet. And so you'll be fine. You'll be fine. All right. So other things about Laplace transforms. They can be useful to solve differential equations, which is why we study them inside a differential equation class. And for this, there's the rules. The Laplace transform of x we'll call capital X. Now, this isn't in the sheet. This is just our convention. The Laplace transform of x prime becomes s capital X minus, and then there's x of 0. And you can also recover, again, this one is not quite in the formula sheet. The formula sheet has the more generic one, but this falls from the formula sheet. Laplace transform of x double prime. That's s squared capital X minus s x is 0 minus x prime is 0. All right, so, but again, this is stuff that you don't have to memorize. It's on the formula sheet, so what you need to do is know how to use it. Now, a few comments, which we've already said in the past, is that when it comes to Laplace transforms for solving ODEs, the initial conditions actually come in at the start. So it's not one of those cases where we say, okay, we're going to work the problem out, and then at the end we'll figure out how do the initial conditions come into play. It's the opposite. Say, hey, we need the initial conditions from the very beginning, and what do? Well, there's a simple process. How do we use Laplace transforms to solve differential equations? And the first step, no surprise, take the Laplace transform of both sides. Then the second step is you solve for capital X, which is, again, not so bad. You just put all the x terms on, all the terms with capital X on one side, all the terms without capital X on the other side, and factor out and divide. And the third step, this is the harder part, is rewrite the expression to be friendly for inverse Laplace transform. What usually shows up on this third step? Yes, partial fractions. So that's one place you might see partial fractions. And of course, it's really preparing us for step 4, which says, all right, take the inverse Laplace transform. And life is good. Now, you might see problems that involve setting things up. Like you might talk about spring problems. You might see mixing problems. Who knows? Who knows? But these are not going to be things that are way out there. In general, I would say that if you've been studying the quizzes are a good source of problems. And nothing is really more difficult than what you've seen on the quizzes. Now, that might either be good news or bad news, depending upon how you feel about the quizzes. But it's news. All right. Any questions about using Laplace transforms to solve differential equations? All right. So the other thing about Laplace transforms is that we have two things we haven't talked about, namely u and delta. So delta stands for the delta function. And the delta function is when you have a pulse. It's like you just do something in an instant. Boom, you hit your system. It's, for example, if you have a spring with a mass on it, you take a hammer and you whack it. And so you say, okay, that's your delta force, your impulse force. So that's what's being captured. And the Laplace transform of the delta function, t minus a, is e to the minus as. Now, we didn't write it down on the formula sheet, but it turns out that this says, look, the delta function only cares about what happens when the input is 0. Okay, so when the input is not 0, the delta function does nothing. So what does that say? Well, it says that if I'm looking at the Laplace transform of any expression, f of t delta t minus a, what do I care about for this function at f of t? I only care about it when the delta function actually says, hey, pay attention. And the delta function only pays attention when the inside is 0. So that says, look, the only thing that matters is what happens at a. And so this is the same thing as f of a delta t minus a. So if you multiply the delta function by any function that's other than a constant, it just says, forget about it, forget about it. It doesn't mean anything. Which reminds me, I forgot to write something down. Jumping back, because I'm allowed to do that, there's one rule that I didn't write down that's not on the formula sheet, but we use it so often, it's probably ingrained into our hearts. If I have the Laplace transform of a f of t plus b g of t, where a and b are constants, what can you do? Yeah, pull things apart. So in other words, this is just saying that the Laplace transform is linear. So this is another nice way of saying, look, if I have addition or scaling, I can pull things apart. I can move constants in and move constants out. So just be ready to do that. I know we've said that a lot, but it's good to keep reminding ourselves. Okay. So that's the delta function. Now the function u, just as a reminder, what does u of t look like? Well, it looks like the following. It's 0, and then it's 1. So that's our unit step function. And what's happening is we like to think of it, or at least I like to think of it, it's an on-off switch. So whenever the input is 0, that's the place where we switch things from going on to off. And why do we like it? Well, the key is it's really useful for piecewise functions. So if we have a function which is defined piecewise, so in other words, behavior changes, then we say, okay, what we can do is indicate behavior change by saying that there's this, at time A, something happens. So that's our on-off switch. We add what turns on, so that's what's happening after A. We subtract what turns off. That's before A. So now when we say after, we should emphasize immediately after. So we only care what's happening at the moment and the behavior immediately before. So I don't care what happened 5 or 6 switches ago. I only care what's happening at this switch. And so if you do encounter things which are piecewise, and you might say, well, how do I recognize piecewise functions? Well, it's just anything where behavior changes. There's lots of ways to express piecewise functions. So you might have a function expressed in terms of a picture, and you might say, oh, well, here's my picture. And you say, oh, well, I have different behaviors. Or you might have a function expressed in this way. It's this part, then it's that part, and then it's that part. And so there's lots of different ways to write a piecewise function. But our goal is to say, look, ultimately, we want to rewrite it as some sort of equation that we can feed into Laplace transform. So that's why we want to be able to rewrite it using this u of t minus a. And if you notice, for the unit step function, there's this nice rule. The Laplace transform of u of t minus a f of t minus a is e to the minus as f of s. So be careful. These have to match. So this t minus a has to match that t minus a. And you might say, well, how do I get there? What if it's not like that? Do I just give up? No, no. There's this nice fact that f of t is f of t minus a plus a, right? The a's cancel. And now, where do these show up? U and delta show up in lots of problems. So like delta shows up a lot in spring problems when you want to whack it with a hammer. Or U shows up in a problem where you're saying that the behavior changes. If you do have a differential equation problem which involves a delta, the delta will become a U in the solution. That's just a note to sort of check your reasonableness. All right. So anyways, that's a summary of Laplace transforms. Now, on a side note, there are 6 problems on this exam. And I will tell you right now that 4 of them involve Laplace transform. So you should be ready to do Laplace transforms. You should be ready to do inverse Laplace transforms. You should be ready to solve differential equations with Laplace transforms. You should be ready to do something else, maybe something piecewise. But you should be ready to handle 4 problems for Laplace transforms. Ideally, you should be ready to handle any problem with Laplace transforms. But at least you know those 4. All right, any questions about Laplace transforms? Okay, cool. So the other topic for this exam is dealing with series. And you'll notice that I'm going to talk about the same problem over and over and over. I just want to demonstrate the ideas here. Because this is the last thing we talked about. We haven't had as much practice. And really when it comes down to series, we're going to be hyper-focused on saying, what's our goal? Our goal is we are told that we have a solution that looks in a particular way. So it looks like this big polynomial, because that's really what a series is. It's a really big polynomial. So we say, okay, so this is what our answer looks like to a particular differential equation, and now we want to understand what we can say about these coefficients. Okay, so that's the idea. Now, if you're keeping track, I've already said there are 4 problems about Laplace transforms, so how many problems will there be about series? 2, very good. So this is the problem so nice, you'll get to do it twice. And so I want to talk about various approaches that you can take to solving these problems, and just to make sure that you're comfortable. And in general, when you're faced with a problem where you have to find coefficients, there are 3 ways you can approach it. One way we spend a lot of time with, one way we hand-waved a little bit, one we haven't mentioned, and I'm going to discourage you from doing it, but I don't want to lie to you and say that it doesn't exist. Okay, so let's start with the first one. So I want to talk about recurrence relationships. And this is the part where it says, hey, what we're going to do is we're going to take our differential equation, and our idea is we're going to feed in everything as a sum, and we're going to combine everything into a single sum. So that's what we're focusing on when we talk about recurrence relationships. Now, what does that mean? Well, we have an example. Let's work the example. So we start with y, and we look here. How many derivatives do we need? 2, because it's a second order differential equation. So we have our y. We'll write that down for reference. 0 to infinity, ck x to the k. What is y prime? Yeah, just take derivatives one term at a time. So I can bring the k down. All right, as k times c sub k, x to the k minus 1. What is y double prime? k times k minus 1 ck x to the k minus 2. I kind of fit. Well, you know what I mean. All right. So there's our y prime and our y double prime, all as sums. And now the idea is we rewrite this differential equation, but for every expression, y prime, y double prime, we replace it with a sum. Now, sometimes we'll have some other stuff. We might have other stuff on the right-hand side. Could be a number, could be a polynomial, could be a function like e to the x, or it could be like 1 over 1 minus x. Probably only those two. Now, you might say, well, why are you picking on e to the x and 1 over 1 minus x? What's special about those? They're on the formula sheet, exactly. We're not going to give you anything that's not on the formula sheet. That's not fair. And, you know, they often say, math, it's the most fair subject of all. All right. Mirror, mirror on the wall. What's the fairest subject of them all? Okay, so sum k equals 0 to infinity, k minus 1, ck x to the k minus 2, minus x, sum k equals 0 to infinity of k ck x to the k minus 1, plus 4, sum k equals 0 to infinity of ck x to the k equals 0. So we've substituted it at our various places. So this is our y double prime. Here's our y prime. Here's our y. All right, so what happens? Well, to do this, we basically need to do two key steps. What are our steps? Do you remember how we make this work? Yeah, same powers. So we want everything to look like x to the same thing. You pick your favorite letter of the alphabet. I've always been using L, but you can pick a different favorite letter of the alphabet. Then we make sure the starts agree. Now, sometimes we get lucky, sometimes we don't. You know, that's life. Sometimes you feel like a nut, and sometimes you don't. But that's okay. Same powers, same starts, and then one sum. Okay. So, what do we need to do to our first sum?
L is k minus 2.
Yeah, L equals k minus 2. All right. What do we have to do to our second sum? Be careful.
Multiply the x.
All right, someone was being careful. Yeah, if you have an x, bring it inside. Now, on a side note, what if this had been, instead of minus x y prime, this had been, say, minus 4 minus 2x y prime? What should we do there? Split in what way?
Two sums.
Yeah, so it become minus 4y prime plus 2x y prime. That's what you should do. So we have ways to handle that. Okay, and now if I move this x inside, do I really need to do anything? Not really, other than I'll just replace my k's by l's. How about here? Bring the 4 in. Do I need to do anything to the power? Not really. I'll just change what I call it. I can change what I call it. That's not a problem. All right. So, in this sum, well, k times k minus 1 becomes L plus 2 times L plus 1. C sub k becomes L plus 2. X to the k minus 2 becomes x to the L. All right. Now, question. Where do we start our sum? We'll end at infinity, but where do we start? All right. Someone suggested negative 2, and then they changed their mind to 0. Could we start at negative 2? We could. Well, could we start at 0? We could. Why is it okay for us to start at either place? Yeah, if you put a negative 2 or negative 1, you get 0. And looking ahead, we see zeros over there. So it's like, cool, we'll put zeros. All right, minus here, the only thing we have to do is change our k's to l's. So it's almost just rewriting L, CL, x to the L. And here, plus the sum, L equals 0 to infinity, of 4CL x to the L. All right, do we have the same starts? Yes, we got lucky here. Now, if we didn't, what would we do? Pull off a couple terms as we need to, so that they would have the same start.
On your second term,
Sure.
L sub straight in for k minus 1.
Well, because it didn't go, L didn't be substituted for k minus 1. See how we have this x? That multiplies and multiplies by every term, gets another x. So it's like x times x to the k minus 1. So when we put this x inside, it really becomes x to the k. So these combine to give x to the k. In other words, like, x to k, we make L equals k. So you notice that there's no more x in front. All right. Well, what's the third thing, right? We see they have the same powers. We see they have the same starts. Now what? Yeah, one sum. So the sum, L equals 0 to infinity of L plus 2, L plus 1, C sub L plus 2. Now here, I see I have an L C sub L and a 4 C sub L, so I can actually put these together as 4 minus L C sub L and x to the L. If you didn't put them together, that would be fine as well. Now, here's the pause. This technique is called the recurrence relationships. If a problem says, find the recurrence relation, you must use this first option. And you might say, well, where is the recurrence relation? Well, what you do is you take this coefficient, and you say, what's the corresponding coefficient over here? In this case, what is the corresponding coefficient over here? 0. So our recurrence relationship would be L plus 2 times L plus 1, CL plus 2, plus 4 minus L, CL equals 0. So if a problem asks you, what is the recurrence relationship, you have to put everything together and say, aha, that's the recurrence relationship. Now, you might say, well, why would a problem ask us this? This is useful if you're trying to understand things such as radius of convergence, or maybe if you're trying to say, I want an explicit formula for, the millionth term. So then you want this recurrence relationship. All right, are we done? No, because they didn't even ask us to find a recurrence relationship. We just found it on the way. What is it we have to find? Yeah, we're looking for coefficients. Okay, so now let's talk about our coefficients. For C0, C1, I claim those are easy coefficients to find. What are they?
1.
Why do you say they're 1? Yeah. So these are initial conditions. Now, you might say, how do I know how many I get? Well, if it's a second order derivative, you get two initial conditions. And essentially, your y0 gives you your c0, your y prime 0 gives you your c1. If it was a third order differential equation, you would get some information about c2. It's not quite c2, but it's close to it. If it was only a first order, you only get one coefficient. So that says how many coefficients do we have left to find? Yeah, we have 3 more to find. C2, C3, C4. Now these are going to come from the recurrence. All right, so how does one do it? Well, you basically start at the very beginning. It's a very good place to start. So where is the beginning here? Yeah, because notice there's this sum starts at 0. So really this is a relationship which holds for L greater than or equal to 0. And I'm really running out of space here. But okay. For L equals 0, what do we have? We have 2 times 1 times C2, so we get 2C2. 4 minus 0 is 4. So plus 4C0 equals 0. Do we know what C0 is? It's 1. So 2C2 plus 4 equals 0. What does that say about C2? So C2 is negative 2. Yes? Using what we know. So the idea of recurrence says you use previous knowledge to help you find the current one. So for example, C2, we use C0. All right, well, what happens next? Well, no surprise, we go to the next number, 1. 1 plus 2 is 3. 1 plus 1 is 2. So that 3 times 2 is 6. C3. 4 minus 1 is 3. C1 equals 0. But we know C1 is 1. So 6C3 plus 3 equals 0. What does that say about C3? Negative a half. All right. And our last one, L equals 2. So notice every time we apply this relationship, we get one more. So for L equals 2, we'll get 4 times 3, which is 12, C4, plus 4 minus 2 is 2, and C2 equals 0. But C2 we know. C2 is negative 2. So I'll go ahead and actually write that down. 12C4, 2 times minus 2, it makes a minus 4 equals 0. So what does that say about C4? C4 is 1/3. And seen. Okay, so we found C0, C1, C2, C3, C4. All right, so that's the idea of recurrence relationships. If a problem ever asks you to find the recurrence relationship, you're going to have to go this route. You grab this, and that tells you how to find coefficients. You just start working your way up one at a time. All right, any questions about that approach? I see a question.
What would the radius of convergence be in this example?
Oh, infinite. Now, you might say, how do I figure that out from the recurrence relationship? Good answer. Good question. You don't. You could. We'd be here a while. What's easier to do is to say, where's the nearest singular point? And so that's something we talked about. Where is the nearest singular point? Are there any singular points? There are none. So how far is it to the nearest one? Infinite. They might be saying, oh, Steve, you haven't mentioned anything about radius of convergence or singular points in your review yet. That's deliberate. Interpret that how you will. And do not interpret that to be like, oh, Steve is really mean. He's a bit of a punk. No. That's not how you should interpret it. I didn't say that. But I'm just saying, interpret that as you will. Okay. So, same problem. This is called cut and paste. Comparing coefficients. And so this is, what is this doing? It says, look, instead of going through all the rigmarole of finding everything, just say, look, I just need to compare coefficients because I know coefficients is what's really happening here. If you jump back to the previous problem, at the end of the day, all we're really doing is we're grabbing the coefficients for powers of x. So the coefficient for the constant term was when L equals 0. The coefficient for x was when L equals 1. The coefficient for x squared was when L equals 2. You're saying, look, instead of wasting our time doing all that, if I don't need the recurrence relationship, I can just grab the coefficients I need. Now there's a question, how many coefficients do you need? And we say we're smart because we say, look, we have defined C0, C1, C2, C3, C4. How many of these are freebies? 2 of them, right? These are initial conditions. It hasn't changed since the last problem because it's the same problem. That means we have 3 more to find. Now C2, this will be the coefficient of 1. C3 will be the coefficient of x. And C4, that's going to be the coefficient of x squared. So I go into this problem thinking, okay, I already have my initial conditions. Life is good. Ba-doo, ba-doo. And I say, look, I only need to keep track of everything up through the x squared coefficient. Everything beyond the x squared coefficient won't matter. So I don't keep track of it. Okay, so we start with y double prime. So remember, what does y look like? It looks like c0 plus c1x plus c2x squared. And I'm going to write a few terms down. c3x cubed plus dot, dot, dot. Okay, y prime will be what? c1, 2c2x, 3c3x squared, dot, dot, dot. Y double prime will look like what? 2c2, 6c3x, dot, dot, dot. Okay, so here's what we're going to do. We come to y double prime and say, all right, I'm just going to grab everything, and I'm going to stop once I hit my x squared, because that's all I need. So I have a constant, 2c2. I have my 6,3x, and I say, oh, I need one more. Can you see the pattern? What will the next one be? So it'll be 4c4x cubed up here, making it 12c4x squared. Dot, dot, dot. And the dot, dot, dot just means parent continues, but those are the higher terms which I don't need. Subtract x. Okay, now I go to my y prime. How far do I need to go with y prime? And why do I stop at the 2c2x? Because I already have an x here. That's going to bump my powers up by 1. It's okay to be generous, but if you're being frugal, you can stop there. And then plus 4 c0 plus c1x plus c2x squared plus dot, dot, dot. And all that equals 0. So we got our y prime, our y double prime. Now what do you do? I'll give you... Yeah, we collect terms. Now, you might say, well, wait, how is that different from here? It's actually not. This is saying group terms together. It's just there's more work. And, who doesn't like more work? So for our constant terms, what do we have? I'll give you a hint. I'm pointing to the first one. 2c2. Anything else? 4c0. Okay, what's our coefficient of x look like? 6c3 minus c1 plus 4c1. So minus c1 plus 4c1 combined to plus 3c1 x plus x squared. We have 12c4. And then what else? Minus 2c2 and plus 4c2. Combined, they make 2c2. And dot, dot, dot. Just means then there's higher order stuff, but we don't care about the higher order stuff because we just need those three coefficients. What does that tell us? Well, what does it tell you about this coefficient if everything equals 0? That equals 0. And this coefficient? And this coefficient equals 0. So now you solve. So we have 2c2, 4 times c0. Oh, that's 4 times 1 equals 0. Aha. c2 equals minus 2. 6c3 plus 3 times c1. That's 3 times 1 equals 0. And we solve c3 equals minus a half. It's not surprising that we're getting the same answers. 12c4 plus 2c2 equals 0. Well, this says 12c4 4 plus 2 times minus 2 equals 0. So what does that say about C4? 1/3. All right. Now, you might say, this feels easier. If you like it, use it. If you don't like it, you don't have to use it. But is there ever a time when you really should use this? Here's some things that basically, if I see anything like a y squared or an e to the xy, something like that, where I have two series multiplying together, this is much simpler. Because once you get two series multiplying together, it gets very convoluted. Oh, that's a little bit of math humor there. Convoluted, you know, right? Convolution, yeah? All right. Okay, that's a very small amount of math humor. Okay, all right. Okay, so that's the second way. Any questions on that? All right, should we do the third way? Okay, the third way, which I do not recommend at all. But again, I'm just going to tell you that it exists so that if someone says, aha, did you know this existed? They're like, yes, but our teacher told us not to do it. All right. Here's what we say. All right. Check this out. Check this out. All right. Y double prime is equal to xy prime minus 4y. Now, how did I come up with that? Yeah, I rewrote it. Okay, nothing too surprising. This is always true. Plug in x equals 0. Y double prime of 0 is equal to 0 times y prime minus 4 y of 0. But do we know what y of 0 is? Sorry, I forgot to put a 0 here. All right. 0 times y prime is 0 minus 4 times y of 0. Well, 0 times y prime of 0 is 0. Y of 0 is 1. So now we know what y double prime of 0 is. And we didn't even break a sweat. Okay, now you're like, that's nice, Steve, but what about y triple prime? Let's step it up, Steve. Can you find y triple prime? And I'm like, okay, I'm up to your task. I'm ready to throw down with you. How do we get to y triple prime if we have y double prime? Take a derivative. So y triple prime is equal to x y double prime plus y prime, so I'm doing product rule, minus 4y prime, which we can say is xy triple prime minus 3y prime. Now, what can we do? We can plug in x equals 0. So we have y triple prime of 0 is equal to, oops, I got too excited. That's a double prime. That's equal to 0 times y double prime is 0 minus 3y prime is 0. But do we know what y prime is 0 is? It's 1. And y double prime is 0 doesn't matter because we multiply it by 0. So now I have y triple prime is 0. And I can keep going. Now you might say, well, how does that help us? Well, Taylor's series says that ck is the kth derivative at 0 over k factorial. So what is C2 going to equal? Negative 4 over 2 factorial. And 2 factorial is 2, so this makes it negative 2. How about C3? Negative 3 over 3 factorial. Well, what is 3 factorial? 6. Negative 3 over 6 makes negative a half. And you can keep going this way. I don't recommend this, but this is like, this thing is so gosh darned ugly, I have no choice. Then yes, this is it. But nothing you'll see is ugly enough to warrant it. All right, thank you for being patient. Have a good day.